Hey guys, okay, so over the next few days we will be making a couple of videos for regarding the CBSE topics for science and maths. Now these videos are meant for people who don't particularly listen in class, and I urge you all to not use this as your study material. Just use this as your reference material for the exams. By the way, this is for the third term only. Hey guys, okay, so for today we'll be doing chapter 11, that's the human eye and the colorful world. So first off, I'm going to start off with drawing the eye. Alright guys, I'm back and I have a picture of the eye. And now as you can see over here, it's clearly mentioned let's see, first you have the crystalline lens. That's basically this entire structure right here. This entire structure is a lens, okay? Yeah, I'm just going to remove this so you can see the beautiful lens. Okay, next you have the aqueous humor. That's basically the fluid, you can say, that's present inside this stuff from here all the way till here. Whatever I've shaded in black, the aqueous humor. It's so funny. Okay, now we have the pupil. That is basically the small little gap you have over here. This small area is called the pupil. And finally the iris, not finally, but yeah, the iris. The iris is basically this and this. So yeah, that's it. Next you have the cornea. The cornea is you can say the outer part of the eye. So you guys have the ciliary muscles that are present right here. Alright, and basically when these muscles they relax, they tend to thin in this particular lens. That's a crystalline lens, which in turn increases the focal length, and hence allows us to see faraway objects. So basically this particular eye right now, it's all tensed, the ciliary muscle tensed, so it can see maybe max here. But when the ciliary muscles are nice and loose, you can see maybe stuff in here, or the distance, or the great distance. Alright, next what else is there? Yes, the retina. The retina is basically, you can say it is a screen on which whatever light falls, it falls on the retina. That is only on a good eye. Like for example, you have a condition called myopia. In that, the image is formed somewhere around here. It's not formed exactly on the retina. Alright, so now you can say the retina, it has taken the light, it has taken the image. Alright, and by the way, the retina, it actually inverts the image. It holds an inverted image only, which it then converts into electric signals and passes it through the optic nerve, that's like right here, you can see it, to our brain. And I'm going to draw a very dumb looking brain. That's our brain. Don't laugh at me, please. That is not a cabbage. Alright, so that's it with the eye. Now we'll go for some conditions like myopia, hypermetropia, and presbyopia. Now myopia is basically the common thing, you know. You have people who wear specs, mostly they can't see faraway objects, they can only see near objects. So basically you can say they're nearsighted. They can only see objects like this close they can see. Alright, but objects like here, it goes more or less like this, you know. Actually goes like this, the image, the light, sorry. Alright, to cure this you need a concave lens present in front of the eye that looks a little something like this. Yeah, goes a little something like this. So basically, even though the light rays come like this, they converge to a point, and that point is our retina. That's over here. However, if this was not present, if the concave lens was not present, then basically light would just go like this, here, and it would just meet around here. Actually not here, but maybe around here. it would meet around there, and that basically makes it blurry to us, makes our vision blurry. Okay. Oh, I believe I forgot to mention the vitreous humor. That's the fluid present inside. Yeah, that's everything inside this. All the fluid present over here, this is called the vitreous humor. Yeah, I should have actually used a paint bucket tool. Thank you. Alright, it does not look like a dinosaur, by the way. Alright, fine. So, where was I? Oh yeah. You have hypermetropia. That's basically myopia, the opposite of myopia. And oh yeah, my bad, I forgot to mention what are the causes of this. The causes of myopia are very simple. It can be either caused due to elongation, that's like basically the eyeball becoming like this, and that looks like a weird potato, I know that, so hold on. Alright, as you can see, the eye has been elongated over here, and this is mostly what causes myopia. And now I am going to move on to hypermetropia. That is basically what hypermetropia is that you have, say, an object over here. This object will be much harder for the eye to for a person to actually see who has hypermetropia, because the image is actually formed around here. It's formed behind the retina. Now in myopia, if you remember, the image was formed in front of the retina, and in a normal eye the image is formed exactly on the retina. Alright, so anyways, getting back over here, actually in this case it should be over here like this and like this. Alright, and for a faraway object goes about like this. The light rays, by the way, this and this, it meets exactly on the retina. The faraway object meets on the retina, not in front. Okay, and now all of this, as you know, the image is converted to electric signals, which are then sent through the optic nerve to the cabbage-like brain. Yes, my brain, this what I drew looks like a cabbage. Okay, anyways, leaving that aside. And finally, the last defect you have is presbyopia. That is usually caused in older people. See, and it is basically the weakening of the ciliary muscles, that's this and this, and also including the lens. The flexibility of the lens, it reduces, so basically the focal length does not get adjusted. So in this case, both far away and close by objects appear blurry. That's like here, and over here it's maybe here like this, and this appears outside. Alright. Oh yeah, I forgot to mention. Alright, so you have people who have both myopia and hypermetropia. For them, the common solution is to wear bifocal lens. Now, bifocal lens, they basically are both concave and convex. Like the upper part may be concave and the lower part may be convex, or vice versa. And I think I forgot to mention about what causes hypermetropia. In case if I did forget, here I'll tell it right now. The focal length of the eye, it reduces. The size of the eye, it reduces, or the focal length actually increases. Both of these together cause hypermetropia. Okay, so next we will move on to refraction of light through a prism. Actually no, basically prism. Just keep it prism, finish. Okay guys, so as you can see, I have made a simple pyramid over here. And now let's count the number of sides it has. One is you have this side. Next you have this side at the back, and one at the bottom, that's like right here. And all three of these, they're rectangular. So basically you can see a prism has rectangular bases. Rectangular. I don't have enough space on screen. No. Okay, it has three rectangular bases, and now you have 1 and 2. That's two triangular bases. Two triangle bases. Okay. Now how about we go into some properties of prisms? Not properties, but like how they work. Yes, how about we go into how prisms work. Okay guys, so to explain the function of a prism, I'll draw a simple prism over here, simple triangle. This is basically the front of the prism. Alright, and now let's say you have some ray of light. Actually, no, to make things more clear, let's take a different color. No, okay, fine, never mind. Let's go for black. That's better. Yeah. Now let's see. You have some random ray of light that falls on it. Now this particular ray is called the incident ray. Alright, and the line from here. Hold on. Alright, so now I'll draw a line that is 90 degrees, that's perpendicular to this, and basically this line right here, you can say it is the refracted ray. And finally you have the ray that actually comes out. That usually this ray is maybe it's a rainbow colored ray. That's not an actual color, but yeah, you understand, it's divided into 7 colors. So that's assuming this incident ray is a white light. Anyways, this ray right here, this ray is called your emergent ray. So basically this ray that comes out is emergent ray. Alright, and if you were to draw a line perpendicular to this point right here, you would get something that is like this. Okay, and similarly if you were to do the same thing over here, you would get something like this. Okay, now let's take this line over here, this line right here. How about we extend this line a little bit, like say like this. Yeah, I know it's not straight at all, but whatever. And you extend this line as well backwards. Now this angle right here, this angle is called, what did I just draw? No, this angle is called your angle of, I forgot, refraction into what a prism does. Well, like I said earlier, a prism basically, if a white light passes through a prism, the white light gets split into several different colors that can be called as right? So basically what is this? Violet, indigo, blue, green, yellow, orange, red. Okay, so first of all red comes first, then comes orange will be around here somewhere, then comes yellow, then you have green, that will be around here somewhere, followed by blue, indigo, and then violet. Okay, and yeah, that's about it. Now say if you want 1 minute, as I was saying, now imagine you want the white light that gets split into this many rainbow colors like this. You want it, say, back into white. So what you have to do, just place the prism inverted, and basically what happens over here is the white light, it forms back and is sent out like this at this angle. So basically your light comes like this and is sent out like this. So you can say that these are more or less perpendicular, more or less. Okay, that's it. Next we can go on to how rainbows are formed. Now how about we go and see how rainbows are formed. Now by rainbows I mean the beautiful little colors you see after rain, after rain. So basically what happens is the sunlight, it basically consists of all the colors you see in the rainbow that are ribbed here, the violet, indigo, blue, green, whatever, all of those colors. So basically what happens is the sunlight, it reaches the raindrops. Now from here it gets refracted a little bit by a small amount, and it goes like here. Okay, you can actually notice that there is a small amount of refraction over there. Now from here it is reflected off the surface, and then it is again refracted. So like around here, yeah, by a slight amount it's refracted. And this particular refracted ray that comes out is your rainbow. That's the Ribgyor thing. The rainbow. Alright guys, so now how about we go into atmospheric refraction. So basically, whenever you see a campfire, or in fact whenever you see a fire, any object you see that is above the fire, as in you see through the air that is above the fire, any object you see, you will notice that it'll be wavering. It won't be stationary. It will have some sort of slight movement, liquid like movement, like maybe something like this, a very fine movement it'll have. So ever wondered why that is? Well, this happens due to the fact that the molecules over here above the fire, they are heated, and hot air is generally it is a lot less denser than cold air. So basically it rises up, and when it rises up, as I've drawn over here, it goes like this. It goes in all sorts of weird ways. So basically when we see through this is what causes us to see a wavy like objects, not stationary objects. Okay, so now you have the same thing, twinkling of stars. Why does that happen? Well, it's very simple. You have the star over here. Now the starlight, it enters the atmosphere of the earth. This is the atmosphere of the earth. This is the earth. Okay, this is earth. Now when this happens, slowly it keeps on changing. So okay, I'll just zoom into this particular portion over here for your convenience. So you have, this is the atmosphere. The light enters like this, and now the atmosphere, it has many layers on it. Those layers, they basically refract the light slowly no, sorry, not like this, slowly at a small angle, because the refractive index is the difference in the refractive indexes are very small. So it does refract the light to a very small amount, or by a very small amount. So now this is what causes the apparent position of the star to be here, because this is what we see. Oh no, wait, sorry, this is what we see. Okay, so the star is over here, but what we see is the star is over here. Now since the star is quite far away, so the ray of light can, instead of being considered as something like this, it is considered as it's considered as a point light. So basically the ray of light, you'll get one ray of light, point sized source. So this is that one ray of light. Now this, since it is a ray of light, it keeps on fluctuating. The apparent position of the star keeps on fluctuating. This is what causes the light to either shine brighter or to become dimmer, which causes the twinkling effect we see. Now this apparent change in position of the star, this is also what causes us to see the sun rise 2 minutes early. So basically this, okay, now I'm going to draw this the sunlight's ray. It's actually more or less like quite a lot, not just a ray, but yeah. Anyways, over here we'll take a ray. So over here when it comes, it actually deviates a little bit. So due to that deviation, we can actually see the sun 2 minutes early, and we can see the sun 2 minutes late when it sets, as in when it comes like around here. The light comes somewhere here, but we can still see it for 2 minutes. This is what causes the delayed sunlight, sunset, sunrise and sunset. Alright, now that we're done with that, let's go on to the Tyndall effect. Tyndall effect is very simple, very easy to understand. All you have to do is say take a beaker. You take the beaker, you fill it with water. Okay, and you mix in something that is partially soluble. Actually no, let's go with insoluble. You mix it in and you pass light through it. Okay, now this direction, this is basically light source, ray of light, sorry. And because of the ray of light actually hitting each particle and scattering and sometimes even bouncing back, you can actually see the particles of the colloidal substance, not of the water. Yeah, it is due to this that you can even see, say, dust when you wake up in the morning, or when you go into a dusty area, into a dark dusty area, and suddenly a ray of light appears from nowhere. You will notice the dust. You can see very fine particles of dust just moving around the room. So yeah, that's pretty cool. Alright, so now let's go into color. Color of the sky and of the sun. Now, have you ever wondered why the sky appears to be blue? Sorry, I should have drawn a blue line, my bad. But yeah, anyways, have you ever considered why the sky was blue? Well, it is caused due to the fact that the sun light that comes onto the Earth's atmosphere, this is the Earth right here, alright? Now, in the Earth's atmosphere, there are very, very tiny particles. This scatters the the colors with the longest wavelength, i.e. red, or say orange, green, all those colors. And at the end, what's left that actually is not scattered? Blue. So oh yeah, by the way, when I say scatter, I mean like it can go like out here, outwards. But anyways, so what's left is blue. So that is basically what we see, the blue color. Due to the same reason, okay, not exactly same, but actually it has something to do with refractive index only. Anyways, I'll show it to you. 1 minute. Alright, so in the afternoon, you must have noticed that the color of the sun is not exactly yellow or yeah, anything like that. It's red. Now this is caused due to the fact that the light that actually enters the Earth's surface, the atmosphere, this light comes from a relatively shorter distance from when it is in the morning. When the sun is in the morning to when the sun is in the evening. The sun does not look like this. I just don't like it. My bad. Okay, anyways, so this causes more the colors of the larger wavelengths to stay, while the colors of the shorter wavelengths get scattered. Okay, due to the many particles you see. Alright, and then this is the Earth's surface, and by the time it reaches here, all that's left is red, and that is what we see. That's why sometimes the sky, that's why the sky also appears to be red at that time, not blue. Alright, and yeah, that's also why the sun appears to be red also, not yellow or anything like that. And that's it, that's all we have for this chapter. So, if you've been listening, hold on, I'll do that real quick. Okay, if you've been listening, you should have understood the human eye, the different parts of the human eye, the different conditions of the human eye, like myopia, hypermetropia, presbyopia, then a prism, the function of a prism, how rainbows are formed, then why stars twinkle, the Tyndall effect, that is basically scattering of light, and finally why is the color of the sky blue and the sun red during the afternoon.